All right, good morning, ladies and gentlemen. We have the last class before you guys depart on a well-deserved spring break. Again, a logistical reminder, after you do come back from the spring break, hopefully reinvigorated, relaxed, refreshed, etc. On April 1st, and that's no joke, April 1st is the first class after the break. We have a treat for you, I hope, with about 90% confidence. I'll change the order of the classes a little bit. We have a chance, or you have a chance to hear directly from Professor Moller, the guy who actually wrote the book, and one of the experts on global warming. He'll come here on April 1st. He'll tell you about climate change, causes, effects, potential consequences. He'll probably tell you about his own research that he has done here in Berkeley with a group of scientists who analyze the data from the thousands of weather stations, temperature measurements throughout the world, well, mostly in the United States, but also elsewhere, correcting for various systematic effects, such as the changes in conditions near particular stations over time, cities building up, the heat island effects and such. So he'll be here on Tuesday, April 1st, and so that means that we are changing the order of the topics. We'll do global warming or climate change first, and then after that, infrared radiation and ultraviolet radiation. That's chapter 9, I believe. Which chapter are we on? This is chapter 8, right? Yes, okay. Right, so we'll do chapter 9 after that. So, which is infrared, ultraviolet, radio waves, etc. So, and then the week after that, April 8th, is your second midterm. So, I guess actually before I launch into this, as you see, we have a lot of demonstrations here. I can again see if you have any immediate questions right now, either about the wave optics or about the geometrical optics that we'll talk about later today, polarization, things like that. We'll cover, hopefully, most of these topics today. If you have any logistical concerns about midterm, please also let me know. The other thing that I wanted to mention, unfortunately, we had a little accident here. I had actually James prepared a cool demo. It has taken him 2 days to prepare. It's a demonstration of a light wave channel. The book actually talks, I think, about the sound channels in the atmosphere, is how the sound bends in the atmosphere depending on the conditions, temperature, etc., which explains how why you can hear faraway trains much further away during the night than during the day. Professor Moll also talks about UFOs and various balloons, etc., which were designed to study these effects. So we were hoping to show you examples of that with light, but we had a little incident. The sugar solution that we've prepared over the last 2 days spilled, so we'll probably do it at some other point. But nevertheless, so that's all that's left of it. We'll give you this at some point later in the semester. In the meantime, we do have a number of optical illusion tricks for you. Here's one as you walk out of the room. Take a look here. There's a little box filled with parabolic mirrors, which is one of the easiest ways to produce optical illusion tricks. I have one more here somewhere that I'll pass around. There it is. Here's another example of a, well, maybe optical illusion, maybe physical effect. I'll actually pass it around. take a look. This is a piece of plexiglass that's well, similar to elements in your glasses. So the glasses are now made out of polycarbonates, not of real glass, but of some polymers. Plexiglass is sort of similar. It has a high index of refraction. So this plexiglass cylinder acts as a lens. We'll talk about lenses later today. And there are two words written behind the lens, dioxide and glass. It's not dioxide, glass is not a thing. Glass is made out of silicon oxide, so it's dioxide itself. Take a look at it and see if you can explain why when you look at the word dioxide, it appears right side up, and when you look at the word glass, it appears upside down. One is in red, one is in blue. Take a look, think about it while I'm talking. I hope to get it back. So, don't run away with it. Pass it around. So these are a number of optical illusion tricks. But before we go into that, last time we talked about wave nature of light. The fact that light under certain conditions can be viewed as a series of oscillations propagating in space, like this. A series of oscillations of electric fields and magnetic fields that sustain each other. The oscillating electric field produces oscillating magnetic field and vice versa. And the whole thing is propagating in space with the speed of light that is about 300 kilometers a second in the normal human units, but in the physicist units it's about a foot per nanosecond. So 1 foot per billionth of a second being the speed of light. So this wave nature of light can be observed directly by looking at the wave effects, the fact that these electric fields that are oscillating up and down, electric fields produced by several sources, add up. In physics, this is known as this effect, this property. The fact that two things add up is known as superposition. That's a fancy scientific word for adding things up. So not just the magnitudes of electric fields, but also their particular directions, or rather the magnitude of the field in a particular direction adds up. And so you can have a situation where one wave, one electric field produces, or one source produces electric field pointing to the left, in another source produces electric field in the same point pointing to the right. Those two can add algebraically so that positive subtracts from the negative, or vice versa, and the two effects cancel each other out. Or if you have in one point electric field pointing to the right from one source, another electric field pointing in the same direction from a different source, those will add up, increasing the size of the effect. This is known as interference. And you can observe it on the surfaces of water, and we can also observe it in light itself. But probably a more important effect, I'll actually show you pictures of interference patterns a little bit later. A somewhat more interesting effect, perhaps, at least from the practical point of view, is the effect known as diffraction. And here's actually an example of this. This is exactly a pattern produced by a laser light as it goes through a small hole. And just to show you that this is a real physical effect, we are not, doing something strange with lasers, so we're not having a source that has an opening of that shape. I will prove to you that this is a real effect. You can see an image of a laser pulse as it passes just through the air without any holes, any screens in front, and produces a nicely collimated circular, roughly, image on the screen. But if I make the beam of this laser beam goes through a small hole, like so, you can see the image spread out. This is exactly a diffraction effect. This is this simple property of, or demonstration of a wave nature of light, the fact that as a light waveform like this, as it passes through a small opening, you can think about this small hole as another source of light, as a secondary source of light. So one can think about what's going on here is you can think that an incident set of waves coming at the hole produce small oscillations inside this hole. And the small oscillations produce secondary wavefronts that are very similar to wavefronts produced by a pebble thrown into a pond. You know, throw a rock into a pond unless you're doing, skipping thing. You throw a pebble into a pond, it will produce wavefronts that come out kind of radially spread out, produce circular patterns from a single point. A very similar thing happens. That if you produce, effectively throw an electric pebble in the middle of this hole, it produces circular wavefronts. And the wave coming out here spreads out. The further you go from the hole, the larger the area this wavefront will cover. And the angular spread, in this case, is roughly of the order of wavelengths divided by diameter of the hole. Now you can think about, you can ask, why is this wavefront coming in parallel, in this parallel, very uniform arrangement like this? And this is what happens when you take a lot of these spherical waves and add them up. If the hole was much larger, then the spherical wavefront from this hole would add up with a spherical wavefront produced a little bit to the left, and another wavefront produced a little bit further to the left. So if the hole was a little bit larger, the angular spread would be smaller as the waves, the sources of the waves spread out over the distance. If the hole is small, the angular spread is large. This is sort of counterintuitive. As you make the size of the hole smaller and smaller, the wave spreads out more and more, because essentially the source of the secondary waves becomes closer and closer to a single point in which you threw a little pebble. So ultimately, for any optical instruments, as it turns out, diffraction is a limiting factor in how well you can see things, the limiting factor in resolution, how well you can resolve or pinpoint something to a single point. And again, this angular spread goes as the wavelengths of light over the diameter. So if the wavelength is small compared to the diameter of the hole, then the angular spread is relatively small. So again, this is an example of what happens to you in sound with sound waves. Sound waves have wavelengths of feet to meters, or maybe sometimes centimeters for ultrasound to meters for normal frequencies. So as this sound with the wavelengths of meters passes through large apertures like doors, windows, it spreads out, because the wavelength is comparable to the size of the hole, and that explains why you can hear people without seeing them directly. If somebody was around the corner behind the door, they could shout, and the wave from their mouth would spread out as it goes through the hole, and then ultimately be able to reach your ear. But light, on the other hand, has a wavelength that's much shorter than this. Light has a wavelength of the order of 1/1,000,000th of a meter, a micron, something comparable to a human hair width, or actually smaller. And so if the diameter is of the same size as the door, that's sort of a meter, wavelength is 1/1,000,000th of that, the angular spread becomes 1/1,000,000, tiny, something that you cannot observe. And so that's the reason why normal objects that are large cast regular, uniform, fairly sharp shadows. To us, shadows don't have much angular spread. That's because the wavelengths of light is small compared to the size of the typical objects. On the other hand, if you pass the light through a small enough hole, if you make the hole the size of, say, a micron or so, then angular spread will be large. In this case, I'm passing this laser light through a little slit produced by I'm getting sticky. The sugar solution is spreading. The hole here is about 20 microns or so, the smallest slit. Wavelengths of red light is 600 nanometers, so roughly half a micron. So the angular spread is on the order of 1 part in 40 instead of 1 part in a million when the light goes through the door. And you can observe the spread. Here's, you can see that the image on the screen is larger than the image I would see if I let the light go undisturbed. I can actually change the size of the hole here. Nope. That's this direction, this direction. So this hole is a little smaller. No, larger, I'm sorry. So this is the smallest slit, produces a relatively large image. I can increase the size of the hole, and the image size becomes smaller. The spread, angular spread, is smaller. If I go through even bigger hole, this angular spread is smaller still. And as I go through a very large hole here, I can see it. It's about 1 millimeter on the side. Well, you can't see this image at all. This image is here. There's the spot. So the larger the holes, the smaller the angular spread is. That's the concept of diffraction. And again, this is one of the clearest demonstrations of the wave nature of light. Nor if the light was a bunch of particles. If the light was just a bunch of little pebbles, they wouldn't behave like this, right? Pebbles, as they go through a hole, don't suddenly deflect. This is the signature property of waves that experience this diffraction. You can also see diffractive effects elsewhere. If you're flying from Rome Airport, take off over the Mediterranean Sea. They have a bunch of sea resorts on the coast. They're quite nice. You can actually see from there arrangements like this where they have a kind of a wall, a wave breaker, something that to protect the nice sand near the beaches from violent waves in the storms. This wall has some openings in it, and these openings produce diffraction of the sea waves slamming into the wall, producing circular patterns of waves that over time erodes the sand and produces this nice semi-circular half-crescent moon shape or half of the round of cheese-shaped lagoons. That's quite cute. This is a picture, you can see it on Google, obviously. There's a website that has these demonstrations of interference and diffraction in under normal wave conditions. Also, the other effect of diffraction is the fact that the waves not only spread when they go through a small opening, but if the size of a object is comparable to the size of the wavelengths, the object doesn't stop or doesn't cast anymore a pure, perfect geometrical shadow. This, in other words, when the wave goes, sees an object that's roughly of the size of a wavelength, that the size of the object is roughly of the same order as the wavelengths of the wave can just go around this object. And objects don't cast pure geometrical shadows. You can actually see waves behind this object, behind the screen. That's another effect of diffraction. The waves can flow around screens and then interfere behind them, producing secondary wavefronts. So this is another consequence of diffraction, the fact that when the wavelength is comparable to the size of the screen no longer casts pure geometrical shadows. I have a demonstration of that as well. Let me switch things here. I can reduce the size of the wavefronts, and here somewhere I have, I probably need to turn the lights off on the stage. There. Actually, this little contraption, this little lens spreads the wave out, in fact. So let me, this is about right. This is about right. Yeah, let's look at the screen. At that screen, we might have to turn the light off too. What you can see is are a number of small objects here in front of the laser beam. You know, a little nail, some, you know, a tip. Something is in the way. This thing. Here's a bit of a wood screw, and they nominally would cast pure, perfect geometric shadows. But if you look very closely, and maybe the camera can zoom into it, or probably after the at the end come close and look. If you actually look very close to the shadows, there are secondary. You know, if that camera on the side can zoom close, the shadow isn't perfect near the outline of the object. You actually see secondary wavefronts. Nah, doesn't come out great. Yes, let's turn the light on. Even the relatively large objects like nails and screws cast shadows that have secondary wavefronts in the region where the normal shadow should be, or in the region where you would expect to see light. You actually see fringes. You see kind of sequences of dark spots and light spots right near the place where the pure geometric, perfect geometric shadow might have been. And this is an effect very similar to this, where the wave flows around the object, producing a series of crests and troughs, spots with very bright, this is the crest of the wave, and the dark spots, fringes, where the waves destructively interfere as they flow around this object. This is another example of diffraction. Now, the last part, the last consequence of the wave nature of light is this concept of polarization and various effects that use polarization. So polarization has to do with the orientation of electric field, or magnetic field for that matter, in space as the wave propagates. And you can sort of imagine this relatively easily. So suppose the electromagnetic wave looks like this. It can propagate forward like so, in such a way that the orientation of electric field is always up. If that happens, light is said to be polarized in the vertical direction. Electric field is always pointing up. I can change direction of polarization by simply rotating the source of the wave, and wave propagating like this, where the B field, a magnetic field, points up, but electric field points in the horizontal direction. This is an example of a horizontal polarization. So the orientation of electric fields turns out to be important for some phenomena. We know this is polarization, so you can have a horizontal, or rather it's called linear polarization, where electric field always points along the same line. This is known as linear polarization. Linearly polarized light can be polarized in the vertical direction, horizontal direction, or at some arbitrary angle. But the point is that the electric field always aligned in along the same line. Or you can have a sort of slightly stranger arrangement where instead of having electric field always point along the same line, you make it form a corkscrew pattern. So if you imagine you taking this E field, and I've broken this demonstration before doing this, so I hope I I'm not going to do it again. So imagine as the wave propagates, the direction of the field rotates. This is sort of what happens when you take a corkscrew. Some of you are not allowed to use one yet, at least not to open a wine bottle. But you know, when you open a wine bottle or you open anything, right, you take a corkscrew, screw it in, the tip forms a circular pattern as it goes into the cork, and then you pull it out. So imagine now electric field being sort of the direction of the tip of the screw. It will form this corkscrew pattern. As the cork follows forward, the tip rotates around, changing the direction as the corkscrew goes in. This is when we arrange an electric field of the electromagnetic wave this way, this is known as a circular polarization. If you looked at the, if I was able to actually see the direction of electric field and I was looking from the back of the source of this electromagnetic wave, kind of like this. If the electric field was linearly polarized, I would see electric field lines form a straight line. If the electric field is circularly polarized, I would see the electric field forming a circular pattern. That's why polarization is called circular. It's actually fairly easy to produce linearly polarized electromagnetic wave or linearly polarized light. In fact, lasers always produce light that's linearly polarized. And then you can use various optical elements to change linear polarization to circular with crystals using phenomena of birefringence or dichroism. Birefringence is the most common. And ask me about this if you're curious. But linearly polarized light is pretty common. In fact, lasers produce linearly polarized light. Your computer screens produce linearly polarized light. Liquid crystal displays are based on the concept of linear polarization. Smartphones produce linearly polarized light. Pretty much any liquid crystal display does. So you can also affect the propagation of the linear polarized light with fairly simple filters known as, again, linear polarizers. Your anti-glare polarized sunglasses use this concept. And let me demonstrate it for you. What happens when a linearly polarized light goes through another device known as linear polarizer. Here, just to make things a little bit easier to see, we have a source of electromagnetic waves, sort of centimeter wavelengths electromagnetic waves. A device known as a klystron produces that. Let's see, this is the detector. Let's see, the klystron's on. At some point, sort of in 10 seconds or so, we'll start to hear an annoying sound. No, that's modulation. Oh, there it is. There's the annoying sound. I have a source of microwaves here. These microwaves are produced linearly polarized. I think and the reason they're produced linearly polarized is that the microwaves are produced by a horn that I know if you can see inside this horn, the source of the microwaves is a rectangular slit. And so it's longer in the horizontal direction than the vertical, and it produces electromagnetic waves polarized, I think, we'll find out, in the horizontal direction. So what it means is that electric field bounces left-right, bounces in the horizontal direction. So if I aim this source of microwaves into a receiver, also has a little opening that's rectangular with the size matching exactly the source of the microwaves with the wavelengths of a centimeter or so. And so this receiver is like a little antenna, that we'll talk about antennas in 2 weeks. This little antenna can detect electric fields oscillating in horizontal direction very well, very effectively, and it converts the intensity of the electromagnetic wave into the intensity of sound. So the antenna receives the microwaves, produces annoying pitch at, frequency of 600 hertz or so. So now suppose that I make the electromagnetic waves go through this jailbar type arrangement. What's going to happen? If I make I guess the waves are actually polarized in the vertical direction. If I make the waves go through a vertical jailbars, the sound stops. This device can completely block microwaves. The reason that it does is that the electric currents are produced in the vertical direction in these jailbars, and it cancels out electric field coming in. And so this jailbar vertically polarized can stop electromagnetic waves that are always polarized, I guess in this case, vertically. If I orient this jailbar horizontally, it doesn't do anything. So it's an example of a polarizer, a device that can absorb microwaves polarized in a vertical direction, and it doesn't absorb them when the microwaves are polarized in the horizontal. If I take two jailbars and crisscross them, making them a really effective jailbar window, such as that a fly cannot escape through them. Now this arrangement of crossed polarizers can stop the microwaves polarized in any direction, because at some point you have a combination of a vertical and a horizontal jailbar, and in fact, independently of the rotation of this, the crossed polarizers stop the microwaves very effectively. So the same concept applies to light, except that you cannot actually see the the little jailbars. Your spiffy polarized sunglasses, or my spiffy polarized sunglasses, otherwise known in late night infomercials as high definition glasses. If you turn on a TV at 2 o'clock in the morning, sometimes there are these infomercials that sell amazing high definition glasses that make everything crystal clear, including reducing glare from the surface of the water. They will sell them for the low price of $9.99 for a pair, or and then you can get a free pair for free if you order one. You can also buy them at a regular store for roughly the same price. This is the normal polarized sunglasses that use materials that also have anisotropy, that are that transmit light non-uniformly. They absorb light when this light is polarized in the horizontal direction, and they transmit light when the light is polarized in the vertical direction. And exactly why this arrangement of horizontal versus vertical will be clear in just a little bit. Your LCD displays are arranged in the same way. The LCD, liquid crystal displays, liquid crystals are a very interesting medium. In liquid crystals, the absorption of particular polarization can be changed by applying electric field. So it's a so-called birefringent material whose birefringence can be changed by applying electric field. And so you can change the absorption by applying small voltages. And so the liquid crystal display is arranged in such a way that there is typically a source of the non-polarized light from the normal sources like normal diodes. This source of light can be visible light. For example, my watch, which uses a digital display, doesn't actually have a light source at all. That's why it can run for years on a single battery. It uses normal light in the environment. It just uses it to scatter the image back into my eye as it reflects from the surface of the liquid crystal. So liquid crystals display works in the following way. They typically have a backlight. If it's a computer display, produces non-polarized light. There's a little film that polarizes this light at in certain direction, in this case, I guess, horizontal. And then you have a body of the liquid crystal which can either rotate the polarization for some liquid crystal displays, or it can block polarization for simpler liquid crystal displays in particular direction, like this watch. If it rotates the polarization, then there's a cross polarizer on the top that nominally the light passing through the horizontal polarizer and the, I guess in this case, polarizer whose polarization is in the screen. Normally, this arrangement of cross polarizers doesn't pass any light at all, unless the degree of polarization is rotated by the liquid crystal when you apply the voltage. So you can apply voltages at small pixels, such that the degree of polarization gets rotated only in a small volume around that pixel. If the polarization is rotated by 90 degrees, then now this light passes through the cross polarizer on the surface, and you see a bright image. This can be done for each color, for each color of red, green, and blue, and this can be done for also for a gray scale image. So these TFT displays rotate polarization, and then there are older liquid crystal displays that would just block the polarization in one particular direction. But the outcome is that the light coming out of the picture typically has linear polarization. In fact, has linear polarization in a certain direction, depending on which direction the top screen is oriented in. It can be oriented along the screen, in which case the light coming out of the screen will be polarized along the direction of the screen. It can be polarized in the vertical direction. As it turns out, Apple engineers are smart enough. They make the polarization to be at 45 degrees. So if you watch your Apple screen in the polarized sunglasses, you can actually see this light from the screen when it passes through if you watch it horizontally. If you flip your screen, you watch it vertically, you can still see some light, but then there is some angle at 45 degrees which doesn't pass any polarization. Looking at it now, I'm actually sad to say that the Apple engineers have changed. This is a new laptop. I bought it about a year ago. As it turns out, it produces vertically polarized light. So I cannot lay on my side, half asleep on the beach and read my computer screen. That's kind of sad. Smartphones. Samsung is okay. It has another layer on top, I think, that converts the linear polarization into circular. And so independently of the orientation of your polarized sunglasses, the image will be visible. You will only see half of the intensity for any polarization. But at least you'll see some intensity. Outside, if you look at Samsung, I had an old cell phone. One of the first smartphones was a Palm Pilot. And then after that, I had a Palm Trio. It had an unfortunate property of producing linearly polarized light, polarized horizontally. Your sunglasses also block any light that is polarized in the horizontal direction, so I couldn't read my Palm Trio screen in my polarized sunglasses. BMW engineers used to produce dashboards in the cars that would emit polarized light in the horizontal direction. That's really a bummer. You cannot drive a Beamer in the polarized sunglasses. That's a bummer. You won't see a dashboard. The more recent models have fixed that. So these are examples of using polarization in technology. Now, actually, let me show you just another demonstration here. Oh, yuck. So I have a polarizer mounted at the top of my computer projector. It's maybe let's turn the light. Oh, there it is. Okay, maybe turn the light off near the stage. So I have a polarizer here on the top, It produces a relatively clear image. The intensity of this light is reduced by roughly a factor of 2 compared to the intensity produced by the light bulb, but you can't notice it. I can place on top of this screen another plastic film. And this plastic, so this is known as a Polaroid film. If you remember the old Polaroid cameras, they use this film known as a Polaroid. It actually has long strands of some molecules that are all stretched, oriented in one particular direction. And this orientation, this long stretch of those inorganic, actually organic rather in this case, long molecules produces an anisotropy in this material, so it passes light on that's only oriented, polarized in one particular direction, in the direction in which these molecules are stretched. So if I place a polarizer and look at the polarized light emitted by the polarizer on the top of this projector, and then rotate this Polaroid film, you can see that the intensity changes. If I cross the two polarizers, in this case, polarization produced by one is exactly perpendicular to polarization that the other polarizer passes. You'll see a black image. If I rotate the polarizer by 90 degrees, you'll see the bright image. And exactly the same thing happens with my sunglasses. I get the dark image this way. My sunglasses are polarized in such a way as to absorb all polarization horizontally. But if I rotate my glasses by 90 degrees, you'll see a more clear image. OK, so now it's this time of the day for me to ask you a question. Now, why is that the polarized sunglasses actually polarized in the horizontal direction? Or rather, why do the polarized sunglasses advertised by late-night infomercials as to produce high-definition images? They're said to reduce glare. And so the question is why? Sunglasses used by fishermen, pilots, and anybody who wants to look cool are said to reduce glare. And so why is that? And the possible answers are because the natural sunlight is polarized, or because the reflected light is polarized, or because UV light is polarized. After all, the sunglasses typically have some UV rating on them, or because sunglasses preferentially transmit only reflected light. So let me start my poll and give you a minute. OK, 10 more seconds. Huh. All right, let's look at the answers. A, B, C, or D. The distribution of answers prefers B. Let me kill that. B is the answer that says reflected light is polarized, which I may have given out by scrolling, but hopefully you remember by reading the book. The reason for these polarized sunglasses to be effective against glare is that glare is an example of reflected light. Light from the sun can bounce off the surface of the water, surface of the road, and then bounce into your eye. Most of the surfaces around the Earth are horizontal. Water clearly surface, water surface is clearly horizontal, so most of the glare that you see will bounce off of the horizontal surface. As it turns out, the light reflected from a horizontal surface is preferentially oriented in the horizontal direction. The reason for this is actually relatively straightforward. What happens is when the light hits the surface of the water, it moves electrons, or it moves the ionized water molecules, and it moves them roughly in the horizontal direction near the surface of the water. And so they re-emit light that is then preferentially polarized in this horizontal direction, in the direction where the electric field is moving the charges. So the polarized light is all that scatters off the horizontal surface is preferentially polarized in the horizontal direction. So if you make glasses that block light that's polarized in the same horizontal direction, you'll reduce glare. You will reduce reflected image, but you will not reduce images or light intensity that comes from not direct reflection, but kind of so-called specular reflection, re-emission from random directions. So that helps. That helps you to look at through the surface of the water, and you look, if you're a fisherman and you're trying to look for fish below the surface, glare really reduces visibility. Your eyes are swamped by the intensity of the light reflected directly from the surface. If you want to look at the light emitted from below the surface, you want to reduce the component that gets reflected off of the surface. And so the way to do it is by polarized sunglasses that will block reflected light, because that will be preferentially polarized horizontally. And then you can see light that gets emitted from below the surface, and its polarization typically is random. And again, we're talking about so polarized, 3D glasses used nowadays, also polarized technology, where you see your left eye has a polarization in one direction, your left, the screen or whatever, the glass for your left eye is polarized in, I broke my glasses. Oh no, well, okay, I'll donate them to physics. The glass polarizes light in one direction for the left eye, in the orthogonal perpendicular direction for the right eye, so that the screen image can shift the images a little bit, produce two sets of images, one polarized horizontally, one polarized vertically. They are shifted a little bit on the screen so that your eyes will see them slightly shifted, then your glasses will block one polarization and the other, so that to create an effect of the stereoscopic projection. The image will look as if it's coming from a three-dimensional image rather than from a flat image. This is done by separating spatially the image on the screen with different polarizations. So the other example of polarization is actually light re-emitted from the atmosphere is also polarized. The reason for this is that a so-called dipole radiation principle, that the light reflected at 90 degrees is always polarized in the direction perpendicular to the direction of motion. So if you look at the light that's scattered at exactly 90 degrees, it will always be polarized in the vertical direction. And you can see that by looking at the sky in your polarized sunglasses. So polarization is the last example of the wave nature of electromagnetic radiation or light. Now, in most real situations in everyday life, we deal with the light that behaves normally, goes on straight lines, and doesn't exhibit the wave property. We call this behavior geometric behavior. The part of science that was developed in the 17th and 18th centuries called geometric optics, which considers light as basically a collection of
Particles considers most normal size objects as being able to cast perfect geometric shadows. So the most fundamental principle that describes geometric optics is this so-called Huygens principle, or well, another one developed by a French mathematician named Fermat, that is described as Fermat's principle of least time. This is the principle that tells you that the light will always propagate along the direction that minimizes the propagation time. So for a light that doesn't have to bounce off of anything, the trajectory, the direction that minimizes propagation time is always straight line. And so this is was understood by Fermat mathematically. He postulated this principle, and this principle is consistent with our everyday observations as long as the wave properties of light are not important, as long as the sizes of objects around which the light or through which the light scatters are large compared to the wavelengths. So one of the examples of this, of using the geometric optics for creating images is the so-called pinhole camera, or camera obscura in Latin, I think. We'll have to, oops. I have an example of that here. Let me see if I can turn this projector off. I have a camera, or have some images, or some objects rather, sources. Here we have 3 light bulbs. I can create a camera by placing a screen with a small pinhole in front of it. You'll have to turn the lights off in order to be able to image these objects. We'll probably have to turn most of the lights off. So here on the screen, you see 3 images, 1, 2, and 3. In fact, if you look actually closely, maybe the camera from the back can zoom in. If you actually see closely, you can not only image the light bulbs, you can image the filament in the light bulb. You see 3 images, 1, 2, and 3, and you actually see this sort of W shapes. This is the image of a filament. This camera is extremely effective. It can produce a very sharp image of small objects. Now, the resolution of this image depends on the size of the iris, on the size of the hole. If I make the hole bigger, more light will come out, but the image doesn't stay sharp. So if I reduce the size of the hole, you can see still images of 3 light bulbs, but you can no longer, you see more light coming out, but you can no longer see the image of the filament. The resolution of this camera depends on size of the hole. And the other thing that you'll notice is that the arrangement of the light bulbs is such as that a single bulb is on the top, the 2 others on the bottom, and the camera obscura, the pinhole camera, flips the image. Right here you see 2 bulbs, image of 2 bulbs on the top and 1 on the bottom. Let's turn the lights back on, and let's look at the computer screen. And this is basically how the camera works. You have a small pinhole. It projects the rays from one side of the object to the back of the box. It projects the rays from another side of the object through the same hole to the back of the box. And just by geometry, you'll see an image that's flipped. So this camera produces an inverted, geometrically inverted image with the resolution that depends on the size of the hole. So if you, the book actually talks about this, and it's slightly unclear on the subject perhaps, so I'll make it a little bit more clear. The book says that if you make the hole smaller and smaller, the sharpness of the image improves. Your resolution, your range of angles that are imaged to a single point, the range of angles that are imaged to one point on the screen depends on the distance between the hole and the screen, that's this distance L, and the size of the hole. So, whether you can resolve on this hole, the two leaves that are separated by, a couple of inches or so, depends on whether the angular distance between those two leaves is smaller than this amount, in which case you won't be able to resolve them, the images will merge. If the angular resolution is better, this number d over L is smaller than the angular distance between the two leaves, they will be projected onto two different spots on the screen, and you'll be able to resolve them with your naked eye a little bit more clearly. So this becomes the limit of resolution. It goes as diameter of the hole divided by the distance between the hole and the screen. And so you can think that you can make the hole smaller and smaller and smaller and smaller, and the image will be sharper and sharper and sharper and sharper. And the book says that, of course, when you do that, the amount of light passing through the hole gets reduced. So ultimately, the image will be fainter and fainter and fainter, but perhaps will become sharper and sharper. So the question is, can this go on forever? Can you make the size of the hole the size of, say, a micron or so, and make the very, very, very sharp image? You guys know? Well, the answer is no. And the reason for this is diffraction. The reason is that this formula, this purely geometric behavior of the pinhole camera relies on the light rays traveling along the exactly straight lines, which only happens when light behaves like normal particles, when we ignore the wave properties of the light. And we can only ignore the wave properties of the light when the sizes of the objects are large compared to the wavelengths of light. When you make the hole of the camera small enough compared to the size of the, compared to the wavelengths, the wave will spread out and will no longer travel exactly on a straight line. And so there's this angular spread depends on the wavelengths divided by the diameter. So notice that the diameter of the hole is sort of in the denominator here. So if you make the hole larger, the resolution due to diffraction will improve. If you make the hole smaller, the angular spread will increase, the resolution will be coarser. That's diffraction. On the other hand, the behavior of geometry is completely opposite. If the geometrical optics tells you that if you make the hole this diameter smaller, the resolution improves, the images become sharper and sharper. So when you start from a large hole and start reducing it, the image will be sharper. This is the regime where geometrical optics works. And at some point, you'll hit the regime where the wave optics will become dominant, and the image will start to spread out and become more diffuse and more coarse, and that's when the wave properties of light take over. And so, and there's an optimum somewhere. And this optimum is given exactly by when this fraction, lambda over d, is exactly equal to this fraction, d over L, and you can make the calculation for you, as it turns out, for this camera, the smallest possible size where the resolution is best is about 1 millimeter. And this is sort of for the distances between the image and between the hole and the screen of sort of a couple of feet. So human eye is another example of an optical element. These optical elements, we know two types of optical elements that behave classically. Something we can talk about lenses, and the human eye has two lenses in it. Well, it actually has one object in your eye has one object called the lens, but there's an additional, there's another lens, and the other lens is the surface of your cornea. Cornea in front, retina is in the back, retina is where your optical image elements sit, the cones and rods that sense intensity and color. Cornea is the curved portion on the front of your eye. As light passes through the front of the eye, it bends the light. You can see this here. I have here some models of lenses I can send the, maybe zoom in on the backward camera on the screen here. I can send a set of parallel rays onto a lens, and the lens can be converging, which will focus the parallel rays into a single spot, or the lens can be divergent if I replace the lens with a lens of a different shape, like this. So lenses can either spread the light out. I'm not sure that it's very visible. We might have to turn the light off at the front of the stage. This light isn't very bright. There you go. Thank you. So a concave lens will spread the parallel light rays outwards. Convex lens can focus them, like so, in a single spot. So here's the parallel set of rays being focused here behind the screen. There, in a spot. So curved surfaces can change the direction of the light rays, and we can use this to either focus or defocus. Can we switch back to the computer screen? Either focus or defocus the light rays. Your eye is designed to do that. So it has two optical elements: the cornea that deflects the light. The shape of your cornea is fixed, so the deflection is fixed. And then the light will be deflected some more by the actual little device called the lens, whose shape can change, the radius of curvature can change, and that will change the focusing of the distant light onto the back of your eye filled with the optical sensors known as rods and cones. So you can focus the distant image that's very far away that produces light rays that are coming parallel to each other into your light bulb. You can focus it on the back of your cornea, producing sharp images. Or if you are myopic and your lens doesn't work very well, if its shape doesn't change enough to focus images from a faraway object, that produces the focuser typically that's in front of your retina, and therefore the image on the retina is a rather diffused blob rather than a sharp point. You know, I'm myopic, so if I take my glasses off, you guys all look fuzzy to me, and that's because the image from you converges somewhere in front of my retina and then spreads out, making a fuzzy blob. And that, of course, can be fixed by placing another optical element in front of my cornea. That's the if I make a concave lens or biconcave lens in front, I can change the size of the focal length. I can focus the image from instead of in front of the cornea to directly on the back, right there. In front of the retina, instead, place it directly on the back of the retina. If you are, so that works for nearsighted people. If you are farsighted, the opposite is true, in which case you want to increase the convergence of the light, so to make it focus exactly on the back of your retina instead of behind the retina. Other optical elements work exactly the same way. You know, your photographic camera has an arrangement of lenses that are arranged in such a way as to focus a distant image onto the photographic film in the old days, or onto a CCD device, a semiconductor device. And again, you can change the distances between the lenses to change the sharpness of your image. that would produce sharp images for objects at a certain distance. Telescopes work exactly the same way too, and there are three types of telescopes. Telescopes that operate using lenses, so these are so-called refracting telescopes, or you can use the same thing with mirrors, with curved mirrors, using parabolic mirrors. They have exactly the same effect of changing the light angle, and producing convergent images onto in a specific place where a human can view the image, or where you can place a photo camera, for example, an array of CCD charge-coupled device cameras. So again, to point this out to you, I have a few parabolic mirrors here. Here they are. And they produce a fake image on the top of this parabola. Come and look at it as you exit the room today. So for these optical elements, the question is, what are the actual resolution limits for an optical element? And we just discussed that in about 5 minutes ago, that if you're building an optical instrument, and this optical instrument has an iris of a certain size, and has the lens of a certain size, and the material quality of certain quality, ultimately the resolution, the sharpness of the image, depends on all of these factors. You can buy a cheap camera, or you can get a cheap camera that's mounted in your cell phone, or you can get an expensive camera. And typically, how expensive or cheap the camera is doesn't really depend on the quality of the image or number of megapixels you get, but often depends on the quality of the optics. You know, how well polished and how purely parabolic the surfaces are in the lens. And the better the lens is, the more expensive the camera is. And these good SLR cameras typically would have better quality lenses and produce better images. The number of pixels does become important at some point. You know, if the size of so you will nominally focus the image onto the back of your retina, or in the back of the photo camera in the focal plane, and how large objects you can resolve sometimes will depend on how many pixels you can put in the back of the camera. So typically, the more pixels or megapixels you have, the sharper the images you produce, but that only works up to a certain limit. Ultimately, the limit of the resolution for any optical instrument will be given by wave nature of light, by this diffraction. And that's given by this formula that ultimately light from any device will spread out, and this ultimately will limit the angular resolution of an optical element or the sharpness of any picture. And this angular spread always depends on the wavelengths of light divided by the diameter of an opening. So in this case, for an optical instrument like a camera, the size of the opening is given by the size of the lens or the size of the reflecting mirror. So this ultimately limits the resolution of any device. The resolution in meters is wavelengths times the distance to the object divided by diameter of the smallest element in the optical system. So typically, this is the size of the iris or the size of the mirror. So if you want to improve the resolution, resolve the objects that are smaller in size, and you're observing them from a large distance. Say you want to read a license plate on a terrorist's car from a satellite. Satellites are limited to how low they can fly, and that you should remember from a few months ago. Satellites typically fly outside of the atmosphere, so they can actually circle the Earth for a sufficiently long time. So the elevation is limited to hundreds of kilometers. So if you know that your distance from which you're observing is limited by 100 kilometers, you want to make the size of your observing area large enough to improve the resolution. So here are a few examples. For example, the Hubble's telescope is probably the best, the instrument with the largest aperture flown to space. It has the diameter of about 2 meters. The diameter of its mirror, of its parabolic mirror, is limited by how big of an object you could have fit into a cargo bay of a shuttle when the shuttle the shuttle program was still operational. So the cargo bay is a few meters across. And so for practical reasons, the diameter of the mirror was limited to 2 meters. And that's for all practical purposes is the limiting case for most satellites in either low Earth orbit or geosynchronous orbit. You can, of course, launch multiple satellites and assemble mirrors somewhere on the orbit from several pieces, but that's engineering that requires difficult engineering. That's technologically difficult. So most spy satellites that are flying have single mirrors. So if you build a spy satellite and the spy satellite is as good as a Hubble, so it may have a diameter of the mirror of about a couple of meters. It absorbs invisible light. So with the wavelengths of 500 nanometers or half a micron, and it flies at a distance of 600 kilometers from the surface of the Earth, the resolution that it may, the spatial resolution on the surface of the Earth is about 6 inches. And that's limited by diffraction. Now, of course, you can make a spy satellite come in a little bit closer, say 100 kilometers. It won't live there very long, but okay, the terrorists also don't sit around in one place long enough, so maybe you can sort of zoom in and then somehow zoom out. So maybe 100 kilometers is reasonable. That will give you a resolution limit of about 1 inch. So, the characters on your license plate are typically 1 inch in size. Some are smaller, some are bigger, but typically 1 inch is a typical limit. So at the best possible conditions, observing at the shortest possible wavelengths of maybe 300 nanometers or so, far blue, will give you resolutions of sort of roughly 1 inch or so at best. And so reading license plate with that resolution is difficult. By comparison, the angular resolution for the human eye is about, when you, again, watch with diameter of about 5 millimeters, the size of your iris, wavelengths of 500 nanometers, is about 1/100th of a degree or so. So if you look at the moon's angular size is about half of a degree. Your eye resolution, limited by diffraction, is about 1/100th of a degree. The real resolution of a human eyeball is actually about a factor of 2 worse than that. That's given by the density of the sensors in the back of your retina. So say 1/60th of a degree or so. The moon is about a degree or half a degree across. So you can resolve features on the moon that are sort of factor of 30 smaller than the size of the moon. So, I mean, you can sort of check it yourself. Go outside and sort of count how big of a feature you can actually see sharply, and they're roughly sort of 1/30th to 1/50th of the size of the moon. On the other hand, the resolution depends on the wavelengths. So if you observe the moon at longer wavelengths, for example, if you observe the moon in microwave band, with wavelengths of centimeters or even millimeters instead of the microns, your resolution would be significantly more coarse. So this is the same image of the moon, but imaged in the microwave frequencies with wavelengths of the millimeter, and of course the resolution becomes more coarse under those conditions. And that again is driven by diffraction. So let's see if, there I have a couple of other things. I'll skip a poll. You can think about it yourself, whether you think spy satellites can read license plate. I've sort of given you the answer. But in a couple of other things to tell you about. So first of all, light slows down when it passes through the medium. There's a quantity known as an index of refraction that measures how much light slows down in any particular medium. Index of refraction is a ratio of light speed in the medium, like water, divided by the speed of light in the vacuums. That ratio is always, for most of the normal materials, is greater than 1. For example, in water, the light is about 30% slower than it is in air. And that fact causes several interesting effects. For example, the fact that the light going into the water tank will refract. And that's again the consequence of this principle of least time given by Fermat. The fact that the light is slower as it propagates to the water means that the angle needs to change if you want to minimize the propagation time between this point and that point. So as the light comes into the water surface, it turns, it changes its angle to a sharper angle, and that's the reason for that is the index of refraction of water that's greater than the index of refraction in the air. At the same time, some fraction of the energy will also reflect, and the reflectivity happens in such a way that the incident angle is always equal to the reflected angle, and that's why you see your images normally undistorted when you view yourself in a plane mirror. As it turns out, this deflection angle, this deflection angle changes or depends on the index of refraction, and some materials have indices of refraction that vary over by sort of 5 or 10% or so over the range of visible frequencies. And most materials, index of refraction actually depends on color, depends on the wavelengths of light. And that causes light to spread out in color as it goes through refractive surfaces like this. So if you send white light through a prism, the prism will refract light by angles that will depend on the wavelengths of light, spreading out the light geometrically in space, producing rainbow colors. This is exactly how rainbows work. Rainbows are reflected and refracted light from spherical droplets of water in the air. Water refracts light differently for different colors, spreading them out in a nice rainbow pattern. And maybe the last question that I'll ask you here verbally is, of course, diamonds are very famous for that. In diamonds, the index of refraction changes by, I think, about 5% or so, slightly less than 5%, for red light versus the blue light. And the diamonds, your jeweler will shape the diamonds with many refractive surfaces, so it can spread the light out in various colors, and you can view it sparkle and see it sparkle from all different angles. As it turns out, the normal diamonds and the artificial diamonds can be tuned to refract the light more for different wavelengths. So artificial diamonds, in fact, will typically sparkle brighter, will produce more visibly pleasing colors or rainbow patterns compared to the normal diamond because they're tuned for a larger variation of index of refraction versus wavelengths. So let me stop here. The book talks about fiber optics that I will probably talk about when we come back after the break. And in the meantime, I'll wish you a pleasant spring break and see you in 2 weeks.